My name is Durgesh Tripathi. I will be talking to you about our own star, the Sun. The lecture plans, or rather lecture plan is like that. So, we will have 3 lectures on the Sun. One will be talking about the introduction to the Sun, its energy generation, and how do we observe the solar interior. In lecture 2, we will be more focusing on the solar atmosphere and various different structures you see in different layers of the atmosphere, and what problems are there in the solar atmosphere, the current science problems which people are working on. And then the third lecture will talk to you about solar activity cycle, solar magnetic field, and role of magnetic field in producing the solar activity. Okay. So, before we start, there are some references which I should give. The first one is the lecture notes by Professor Solanki, which was given by him in International Max Planck Research School. So, there is a website, you can look at those slides. Some of those slides I will be using. Then there are 2 different textbooks, Physics of the Sun and Solar Astrophysics. The first one is written by Dermot Mullen, CRC Press, and the Solar Astrophysics by Peter Foucault. And these should give you overview of the whole solar astrophysics and various problems and their current understanding. Now, let us start looking at the Sun and its introduction. Let us start by asking a question that why do we study the Sun? Now, the first thing comes in your mind is that the Sun is the only source which provides almost all the energy to the humanity, right. So, all the energy which is coming from the Sun is coming out to the earth, and all these plants, vegetation, animals, yourself, everybody is sustaining life because there is energy which is provided by the Sun. Now, any activity which takes place on the Sun, it could be also devastating for us, and that affects humanity to a large extent. And one of the examples is like when there is an eruption from the Sun, all these energetic particles, they can travel all the way into the interplanetary medium, comes into the Earth's atmosphere and could produce electric power blackouts, all the satellite communication can go off, and so on and so forth. And here is an animation which essentially shows that how the solar energy travels through the interplanetary medium, and thankfully we have the magnetosphere which stops all the high energy particles. Sometimes these particles, they penetrate through the Earth's magnetic field and produce these kind of aurorae, which you very nicely see from North Pole, for example, Aurora Borealis, and this is an example taken in Norway. In addition to the humanity effect, the Sun provides natural laboratory to study different branches of physics, and I will elaborate on that in the next slide. But to give an example, that essentially this is a normal star which can be resolved really well because it is so nearby that you can use a telescope to look at the scales which are at which the physical processes are taking place. So, here is an example taken from the Solar Dynamics Observatory, and you have an image which is showing all these fundamental scales, fine threads of structures where a lot of physical processes in the Sun's atmosphere is taking place. Now, I mentioned the Sun is a special star because it is close by to us and it is providing energy to us, but it is also an ordinary star when you think in terms of all the other stars you see in the Milky Way, for example. Here what we plot on x axis is the surface temperature of all the stars we see in the Milky Way, and on y axis is the luminosity from all those stars. And what we find that most of these stars, they follow one particular line which we call main sequence, and there are other patches in and around this plot, and that essentially shows how different stars they form and evolve and so on and so forth. So, in this plot, the red circle essentially shows the Sun, which tells you that Sun is nothing but just an ordinary star which is in the solar system, and it is in main sequence, and main sequence essentially means that the stars are in the phase where at the center they have hydrogen burning going on. and that is providing all the energy to the stars. This plot also tells you that it's a G2 type star. That essentially tells you that how hot and how big the sun could be, and the age of the star is about 4.5 billion years. How is the study of sun could be related to various other branches of physics? So, here at the center the image of the sun, and let us try to see what other branches of physics could be connected to. To begin with, we start with sun earth relations, climate and space weather. So, as I mentioned in the beginning, sun provides all the energy to the earth, and so essentially the whole all the activities which happens on the earth is based on mostly on the, because the energy is provided by the sun. So, sun earth relation is a very important important subject to study, and because sun also defines what the climate is going to be, and with all these new satellite communication, astronauts going into space, we need to worry about space weather and sun climate. Turbulence and dynamos, for example, sun has its own magnetic field and it has lot of turbulent features which cannot be produced on the earth, because the parameter space the sun provides is really different and large. Therefore, one can observe the sun, use the sun as a laboratory and try to understand the turbulence and how actually the sun produces magnetic field via the process of dynamos. Plasma physics, sun is fully ionized plasma, and it gives you an idea about how the plasma is confined, how its various other plasma processes are taking place in such an hot and dense environment. Atomic and molecular physics. So, sun provides an opportunity to detect various different elements. For example, helium, which is the second most abundant element in the universe, was detected first during a solar eclipse spectra taken. And in addition, the other high ionized heavier elements, for example, iron, like 13 times ionized iron was first detected into the eclipse spectra. Fundamental physics, neutrinos and gravitation. So, neutrino was detected, or in the solar model neutrinos are produced and during the solar reactions, and they have been detected. And actually by observing the solar neutrinos, it was found that they have tiny mass, and that helped them oscillate between the three different flavors. Gravitation, the first proof for general relativity came through solar eclipse by Eddington. The cool stars, so sun is essentially a normal star. So, if you study the evolution and structure of the sun, you would be able to say a lot about other stars which appear as a point source, and you do not resolve very many things on its surface. In addition, we have all these planets which we observe, and with the ongoing field of extrasolar planets, it is really important now to study how our planets formed and how do they evolve. In addition, all these cosmic rays, interstellar medium, and so on and so forth. So, study of the sun really provides a connection to study other branches of physics. Now, in the solar system, if you add all the planets, sun contains the 99.8% of the total mass, and which is about 1,000,000 times the mass of the earth. So, here everything sun as well as all the planets are put on a scale, and that tiny dot essentially is the earth, and the radius of the earth is about 700,000 kilometers, which is about 109 times the 109 times the radius of the earth and twice the distance between moon and earth. Now, what do we know about the sun so far? Now, as a child, you draw sun like this. So, you have a orange ball with all these flames coming out, and if you are happy child, you put goggles on that. But now, when you observe the sun with a telescope, what we see that the sun is just a bright orange ball with some tiny dots on its surface, which they are called sunspot, and we'll talk about these sunspots in the next lecture. But what you also see that the around the limb of the sun, so the center is called, I mean the sun appears as a disk when you observe it in 2D. So, the outer region is called the limb, and towards the limb you see there is a uniform darkness, and that is essentially because of the limb darkening, which we will talk about again in the next lecture. But here is, this is what when you see when you look at the sun from ground with a telescope. By using all the theoretical models and all the understanding we have so far, this is a artistic version of how we can put in the sun and all its structures together. So, what we know now is at the center of the sun there is a bright source, that is where you produce all the energy. The energy is then radiated away, and the radiation is the dominant way of transferring energy up to the 70% of the solar radius. In the top 30%, the convection takes over, and that is what you see as a upper darker areas like so here. So, that is your radiation zone, and then you go further away, then you see this is the convection zone, and then when you go out, then you start looking at the surface. The convection, you can look into some different spectral lines. So, for example, here is an animation which is essentially taking different images at really fast time cadence and put them together, that actually makes an animation. And what you see that these are the granular patterns. So, you see these bright blobs which are coming and going, but they are surrounded by these dark lanes. So, that essentially shows that the energy is being brought out by these blobs, the hot bubble, and then essentially it is just cooling down and going inside through these dark lanes. That essentially is in if you compare that boiling water in a kettle in your kitchen. Now, when you go higher up and start observing, as I showed earlier, what you see is the solar surface as an orange ball, which is called the photosphere. And again, it looks like an orange because it is a visible light, it peaks around 5,500 angstrom. If you again use the same telescope and you use a filter like in your camera when you use different kind of filters to take pictures, here what you do, you take a filter which is only collecting photons at a particular frequency. So, if I use a filter to just collect photons which are being emitted in at the wavelength where the hydrogen alpha line is sensitive to, what you would see is the chromosphere. And what you find in this is that there are bright structures, but there are also dark structures on the disk of the sun. Here you have these dark structures, they are called the solar filament. Now, why they are dark? Because they are essentially plasma which are hanging into the atmosphere, and in the background you have the bright light which is coming, and these cooler structures are essentially absorbing these photons and appearing darker. Now, the same structures you see when you see them on the limb, for example, here there is this bright structure of the limb, they are essentially the same features as these dark ones, but now they are being seen in emission because there is nothing in the background which is emitting, and these guys, they are emitting their own light rather than absorbing something else. So, they are called the solar filaments and prominences. The other part of that structure of the sun you see when the moon comes and blocks the disk of the light of the disk, and you start seeing the outer atmosphere which is extending far beyond up to 5, 6, 7 solar radius. What you see is a crown like appearance, that is called the solar corona, and there are a lot of structures you see in this. So, here these are the structures which you see coming out of the sun, and it is going all the way till about 6, 7 solar radii. Okay. What you also see that there are structures here where things are open quite a lot, right. They are going all the way connecting to upper outside the sun. They are called the plumes, and that is the axis of the sun on which around which the sun rotates. Okay. So, that you see when the sun has blocked the disk, because the outer region of the sun is about 1,000,000 times less bright than the disk itself. Therefore, if you essentially it is like lighting two bulbs, one is 500 watts and one is 2 watts for example, and you light them and look at them from far away, all you would see is the 500 watts light, not the 2 watts light. So, you have to switch it off the 500 to see the 2 watts, and that is what essentially moon does. And fortunately, the angular size of the moon is essentially exactly the same as the disk of the sun, which essentially blocks the light in the photosphere, from the photosphere. And you see this in white light, because what we know now is that the light is coming from the photosphere itself, but they are getting scattered by the free electrons which you have in the upper atmosphere, which is the corona, and we will talk to you more about it in the next lecture. Now, let us look at the structure of the sun. So, what we know so far: solar interior, solar atmosphere, solar wind and heliosphere. So, this is again a cartoon picture put in, and what you see that there is an interior of the sun, that is where your nuclear energy or nuclear fusion is taking place. The energy is radiated away up to about 70% of the radius, and then you have the convection taking place, and then the energy is then flying off, or the photons are essentially flying off into the atmosphere. Now, whatever we see from there inside is called the solar interior. So, what we see is the photosphere, and above photosphere is the solar atmosphere, and beyond the corona, which is the outer layer of the atmosphere, we have the solar wind, where all these energetic particles are going and flooding the interplanetary medium, and essentially it becomes heliosphere, where you take the whole the effect of the sun, the sphere of influence of the sun is called the heliosphere. Now, if we put in all the parameters together, what we find that between the core and corona, the sun presents a wide variety of physical phenomena and processes. For example, the gas density varies by 30 order of magnitude, and the temperature by 4 order of magnitude. And the relevant time scales are from 10 to the power minus 10 seconds to 10 giga-years. So, 10 to the power minus 10 seconds comes from actually the rate at which the nuclear reactions are taking place, and 10 giga-year essentially comes from the total age of the sun. You need to have really high density and high temperature for the nuclear reactions to take place at the core, but then you have very less density outside on the surface, where the photons which are being generated inside the core, they take about 1 million years to come all the way to the surface, and then they are flying off and coming to you. There is a huge difference, about 30 order of magnitude, when you go all the way from the core into the heliosphere. Okay. So, since physics at different scales could require a different technique, so in order to understand the sun and its atmosphere and solar wind and heliosphere, we need to employ different observational and theoretical techniques, and such are like nuclear physics, helioseismology, spectroscopy, polarimetry, etc., etc. Now, let us look at some of the vital statistics, which is very important, and we will be using it later on. The first question you would like to ask is the sun solid, liquid, gas or plasma? What you need to look at is how dense the sun is. So, what we find that the average density of the sun, I mean, we know that of course, the solar core is very, very dense, the solar atmosphere is very, very less dense. But if you just take an average density on the surface somewhat, then what you find is that it is 1.4 grams per centimeter cube. Now, the average density of the earth is about 5.5 gram per centimeter cube. What is the mean density of water? That is 1 grams per centimeter cube. So, this is denser than the density of water, and what we know now is like it's made of plasma, and the best example to see plasma is either the thunder lightning you have, or even look at the candle. When you light it, the flame essentially represent plasma. The second question then you would like to ask is, what is the chemical composition? What is the sun made of? What is the chemical composition of the sun? And that you find by using a spectroscopy. So, the composition and temperature and the pressure of the photosphere is revealed by the dark Fraunhofer lines in which you can identify about 20,000 of them. Right. So, here is a Fraunhofer spectrum, and what you see that different of these lines are mentioned, they belong to different elements. And essentially, because when the light is coming, the sun is radiating or giving photons at each and every frequency, that is why you see this continuum. But on top of that, you have these dark lines which are missing, and that is missing because the photon at that particular frequency is absorbed by something else, and every element can only absorb a photon at a given frequency, because that depends on that particular element. You can find that what elements these lines would belong to, and therefore, you can find the composition. Similarly, in one of the solar eclipses, you can find you observe the emission line spectra. So, in addition, instead of having these dark lines in emission line spectra, what you will find essentially the bright lines above the continuum, and this is how helium was discovered in the solar eclipse spectrum. Now, the third question, what is the temperature of the sun? Can you measure the temperature of the sun? Yes, of course, you can measure the temperature of the sun. What you do, essentially, you look at the solar radiation spectrum, and what is done here is the red one is essentially the spectrum on Earth. So, where you see some of these are absorbed by different molecules like water, for example, oxygen. But if you go to the space, then you can get all these radiation, and then you try to fit with a black body spectrum, because that is that gives a unique curve for a given temperature with a peak at some particular wavelength, and therefore, you can figure out what the temperature of the sun would be, or like any black body. If the sun was a black body, then the temperature of that would be about 5,800 Kelvin. The other way you can look at the temperature of the sun is like, if you know the luminosity, you know the solar radius, then you can use the Stephan-Boltzmann law, and of course, considering again as a black body, then you can work out what the temperature of the sun would be like. Let us take the next question. Does the sun rotate? And if it does, how does it rotate? The sun rotates differentially. At the equator, it takes about 25 days, which rotates at faster than the pole, and at the pole it takes about 35 days. Now, it has very strong implications when it comes to producing solar magnetic field, which again we will take it up in the second or third lecture, but sun does rotate. And also what we know, that the rotation axis of the sun is about 7 degrees tilted from the vertical. Now, the last question we will take is, what makes the sun shine? Now, that is a very, very important question, because we need to understand how does the sun shine, because that would lead to understanding of how does sun produce energy, right. So, let us quantify this question. A total energy output from the sun is around 3 into 10 to the power 26 joules per second. Now, each square centimeters of the sun's surface is about 600 times brighter than a torch. We also know, essentially you can work out, that the sun delivers 1.36 kilowatt per meter square at the top of the atmosphere of the earth. So, that is called solar constant, and we know that solar constant is no more a constant in that way. It does have some variation, but very, very tiny, only 0.1% over a solar cycle. In 20-30 minutes, the sun provides to earth the yearly energy needs of humanity. The total worldwide energy consumption per year is 500 exajoules, which is 5 into 10 to the power 20 joules. Now, you can imagine, take this energy, which is 500 exajoules, and how much sun produces every second, and that is why solar energy is very, very important. Now, the question is that how does sun manage to generate its own supply of energy, and we know that this is possible because of nuclear reaction, and nuclear reactions take place at a temperature of 15 million degrees. Let us look at it in more detail. How does it work? Now, we know that the sun is a self-gravitating body. Now, it works like this. If somebody takes a really heavy ball, then the weight overlying the material the weight of the overlying material crushes center portions, right, because the whole ball is essentially collapsing. So, it is like if there is a very heavy ball, the guy who is holding this on head will be just crushing, right. So, it is essentially if there is a big ball which is self gravitating, then everything will be trying to collapse, and that collapse will lead to compression, and that leads to high temperature, like filling when you fill air in your cycle tire. And that leads to high density and high temperature that essentially starts the nuclear fusion. Now, we know all the solar parameters. Can we work out that does it really lead to the enough temperature for the solar fusion to start? So, let us look into it. The pressure at the center of the sun equals the weight per unit area of the material on top. Now, if we consider G be the average gravitational field felt by such a column of material of mass per unit area m. So, in order of magnitude we can work out what small g is, which is g m over r square, and mass per unit area essentially is mass divided by radius square. If we plug that number in, what is mass of the sun and mass of the and the radius of the sun is, then we can work out the pressure at the center, which is essentially mg. Again, order of magnitude calculations, we find that the center pressure is 2 into 10 to the power 17 grams per centimeter per second square. Now, the pressure of the perfect gas is associated with the random thermal motions of particles, which is making up the gas, right. So, we can use ideal gas law, and we know that P equals to nkt. We can put in all these number where we consider n to be 1.4 grams per cc on the average value. So, at the center the density is about 110 times larger, then we can use the central density as 150 grams per centimeter cube. And if we put in all these number, what we find, the temperature at the core comes out to be 15 million degrees, and this is sufficient temperature to start the nuclear fusion. Reacting particles, although the temperature is about 15-16 million Kelvin, the total energy of these reacting particles, which is kT, is essentially about 1 keV, that is thermal, and that gives rise to the term thermonuclear reactions, in which the light nuclei in the sun fuse into heavier ones. And due to this fusion, there is a slight loss of mass that occurs in the fusion reactions and emerges in form of kinetic energy and energetic photons. Now, which reaction is dominant? We know that the nuclear reactions happen. What kind of reactions happen? And if we know what kind of reactions are happening, there could be many, we need to figure out which are the dominant reactions. How much energy is liberated in each reaction? Because essentially we need to fulfill the solar constant or the solar luminosity. So, we need to understand how much energy is liberated into each reaction, and once we know that how much energy is liberated, then we also need to know that how many such reactions can happen or should happen to power the sun and give it energies, which is the luminosity. Now, we know that there are two different type of reactions. One is the PP cycle, which was discovered and suggested by Bethe and Creutzfeldt, and the other is the CNO cycle, again suggested by Bethe, but it was found that the CNO cycle works only 0.5% times, or it only powers the 0.5% of the sun's energy output. But CNO cycle, we know that it is very, very important when it comes to the hotter stars. But in this, for the sun, PP cycle is the most important one. In this cycle, what happens is the most of energy is generated through the PP chain reaction, whereby you have two hydrogen coming and merging, and then a separate reaction the two hydrogen, and essentially giving to the PP chain, which I will come into the next slide. But what happens in this cycle is the total yield is about 26.7 million electron volt per helium nucleus and neutrinos. So, in this reaction, the aim is to fuse hydrogen into helium plus get some light plus neutrinos. And in these reactions, only the 0.7% of the hydrogen mass gets converted into energy, which actually powers the sun. Let us look into it in a bit more detail. So, there are three paths actually the reaction can take place. So, you have a PP chain where two protons are coming together and they form 2H, and then 2H can take another proton, it forms 3He. The two protons can also take another electron and then form 2H and gives you an electron neutrino. Right. Then the other path could be that these reactions where you have this 3He forming can take another proton and gives you helium right away here. It is called the PEP and HEP reaction, whereas you can also have these reactions where you have 2H and one proton giving you 3He, and then these 3He could essentially combine together and gives you beryllium. Now, let us look at these reactions indifferently in this table. What you have is PP1, PP2, PP3. PP1 is a three-step reaction where you have two protons coming giving you electron neutrino, a positron and a deuterium, and then a deuterium can combine with another proton, gives you gamma ray and helium, and then a 3He, not helium, 3He, and then 3He can combine with another 3He which is coming from parallel different reaction, which gives you alpha particle which is 2He4 helium plus two protons. What could also happen that the 3He which you produced in the second step of PP1 does not combine with 3He you produce parallelly, but it combines with an alpha particle and gives you gamma ray photon and a beryllium. Now, this beryllium can take another electron, converts itself into lithium, and then lithium takes another proton, converts into alpha particle. But the second step of PP2 can be replaced again by another reaction which is called PP3, where the beryllium can take another proton, forms the gamma ray and converts itself into boron, and then the boron converts again into beryllium, and beryllium can then convert into alpha particle. Now, these all reactions are possible, but when you look at the branching ratios, that essentially tells you the probability of these reactions to take place. What we find is that the first reaction, that is PP1, where this three-step reaction is the most possible one, and it happens about 87. The ratio for first versus second and third together is 87 to 13, and when you compare second to third, then it is 13 versus 0.015. So, the PP1 reaction is the most important one for the sun currently. Now, let us look at this in more detail, that the PP1 is by far the most important reaction, and the total mass which gets converted into energy is 10 to the minus 3 plus 5 into 10 to the minus 3 and 10 into 10 to the minus 3. That essentially is the mass deficit at three different steps which you find, and it is an atomic mass unit. You can convert that into total energy, and that you find is the total yield is 26.73 MeV. Some energy is carried away by neutrinos, which is about 0.4 million electron volt. So, the energy available through PP1 chain to power the sun is 26.25 MeV, which converts into 4.2 into 10 to the minus 5 ergs. Now, what we know that the solar luminosity is 3.84 into 10 to the 33 ergs per second. So, can we work out how much energy or how many reactions has to take place? Total reaction per second is the total luminosity divided by the energy you produce in one PP chain reaction, which is 3.8 into 10 to the power 33 divided by 4 into 10 to the minus 5, and what you get is the number 10 to the power 38. So, at the core of the sun, every second there are 10 to the power 38 reactions taking place, and during this reaction about a billion ton of protons are fused per second to form helium. Right. So, so far so good for the nuclear reactions, but what you produce into nuclear reactions? You produced helium, you produce heavier elements like lithium and boron. They essentially get converted into helium, into this pp2 and pp3 chain reaction. What you also produce is the photon or the gamma ray photons you produce, and these gamma ray photons essentially they go through various collisions within the solar interior, and it takes about 1,000,000 years to come all the way to the surface and gets ejected as light, which comes to you. In addition, it also produces electron neutrinos. What happened to those electron neutrinos? In all these reactions in PP, in PP1, PP2, PP3, in PEP, HEP, and in all these reactions you do produce neutrinos. So, let us look at neutrinos. In this plot, on the x axis is the neutrino energy, in the y axis we are plotting the flux at 1 AU. So, you take the standard solar model, which essentially takes all the nuclear reactions into account and tries to predict the spectrum of solar neutrinos as a function of energy at a distance of 1 AU from the sun, right. What it shows is the neutrinos which emerge from reactions involving only 2 outgoing particles are emitted at unique energies, which they appear as lines in this plot. So, for example, this line, there are vertical lines, these are essentially at one particular energy, and the reactions with more than 2 outgoing particles, they give rise to a continuum of energies with well defined cutoff, because that cutoff is determined by difference in the energy between the initial and final stages. So, what happened to these neutrinos? If we work out, then the mean free path of these neutrinos, which is L equals to 1 over sigma multiplied by density, where sigma is the collisional cross section and the density, which is the core density at the core. We put in all these number particle density and cross section. What we find that the mean free path of these neutrinos is about 10 to the power 18 centimeters. The radius of the sun is only about 10 into 10 to the power 10 centimeters. What it means? It means that the neutrinos which are generated in the core barely feel the material of the solar interior. That essentially means the sun is essentially transparent for the neutrinos. They travel with almost speed of light and they reach the solar surface in only 2.3 seconds. And we know that how many reactions are taking place per second, and that many neutrinos are being produced. So, the sun generates about 2 into 10 to the power 38 neutrinos, pp neutrinos per second, only pp neutrinos. So, the flux is even more. So, at a distance of 1 AU, we can work out how many pp neutrinos are arriving, and we find that the flux is n divided by 4 pi d square, where d is 1 AU. We find that at a distance 1 AU, we have 6 into 10 to the power 10 neutrinos per second per centimeter square. So, you take your body 1 centimeter square area on your body, and that area is being crossed by 6 into 10 to the power 10 neutrinos per second. Now, the question is that can we detect them? And there have been a lot of efforts made in the past to detect these neutrinos. So, here is the first experiments which was done by in Homestake gold mine by Raymond Davis, where he used chlorine, and when neutrinos they come interact with chlorine, they change into argon, and then you can use these argon to count how many neutrinos have arrived. Then there was another experiment where you have the super Kamiokande and followed by the super Kamiokande, where you use water, and essentially you look at the bulbs lightning as and when the neutrinos are coming. And finally, which solved all the problem is the Sudbury Neutrino Observatory SNO that was in Canada, which used heavy water instead of water or chlorine. So, let us look at this. If you look at the plot which is produced from using the solar standard model, each neutrinos produced in different cycles, they have different energies. So, you need to have different detectors, for example, gallium, chlorine and super Kamiokande, to detect different energy neutrinos. So, different experiments are designed to detect neutrinos at different energies, and if you look at those neutrinos detected. So, here in the plot, which in the left is the chlorine, in the second from the left is using water in Kamiokande, and then you have the gallium detector, which essentially here, and then you have the heavy water with Sudbury in Canada, and here is what is looking at all the neutrinos differently, and here they are all made to look at the electron neutrinos. The only one which was looking at various other all the other neutrinos which were supposed to be present. Now, the standard model predicted about 8.1 solar neutrino units. Now, what is one solar neutrino unit? Is the solar neutrino unit is 1 neutrinos per 10 to the power 36 target atoms. Since 1968, the home stake, which used the chlorine as the detector, experiment has given a value of 2.5 plus minus 0.3 SNU. Now, this is a factor of 3 to 4 is smaller than what was predicted from the standard solar model. Now, the chlorine detector worked like you have essentially using this chlorine which gets converted into argon, and you essentially count how many argon elements or argon atoms you have to work out how many neutrinos you detected. So, that became a solar neutrino problem, because standard solar model predicts about a factor of 3 to 4 larger solar neutrinos than what you detect. Later on, when the gallium detectors and Kamiokande and super Kamiokande detectors were used, still the neutrinos were missing. The gallium experiments found low neutrino flux, even including neutrinos due to the PEP reactions. So, earlier the chlorine was only to look at the neutrinos which were in PEP reaction, but gallium also looked at the PEP reaction and the neutrinos coming out of the PEP reaction. The Kamiokande and super Kamiokande in 80s and 90s, they looked at the neutrinos which are coming out of the boron neutrinos. So, the neutrinos coming out of the boron nuclear reaction, and they still found that half of the neutrinos were missing. Now, the resolution of the problem came when the Sudbury Neutrino Observatory in Canada used heavy water, and it detected the right number of neutrinos, and that was a big achievement for the standard solar model, where it not only detected the electron neutrinos, but also the mu and tau neutrinos. What was also found that the electron neutrinos convert into mu and tau neutrinos on the way, because it has a small mass which allows it to oscillate between 3 different flavors. It was first proposed early on in 59 and 50s and 60s, but people were still not believing to it. And this gave some confirmation was obtained by measuring the anti-neutrinos from power plants with super Kamiokande. So, that confirmed the standard solar model, and for that Raymond Davis Jr. was given a Nobel Prize in 2002. He was the first one to start looking at the solar neutrino observatory using chlorine. Now, the solar interior. Can we observe the solar interior? One way to look at the solar interior is to look at the neutrinos, but the other way to look at the solar interior is to look at the oscillations and employ the technique helioseismology. Helioseismology is essentially taken from seismology of Earth, and this is seismology for sun. So, helium means sun, helioseismology. What essentially you do in this, when you look at the sun as a star and you have a long time series of observation, what you find that the entire sun vibrates from a complex pattern of mainly acoustic waves with a period of around 5 minutes, which we call them P mode. What you see in the plot is essentially taking the sun as a point source and observe and look at the Fourier power spectrum. What you find is that there are different peaks in the frequency, right? Power is located in different frequency bands, and that frequency is peaking at around 3000 microhertz. That essentially converts into a 5 minutes period, and that is why it is called 5 minutes oscillation. Now, the oscillation is best seen as Doppler shift of spectral lines, and you can do that, take the Doppler shift by measuring spectral lines and continuous observations, and this is an observation taken from SOHO MDI, Solar and Heliospheric Observatory, and what you see that each point is wobbling, that essentially shows the plasma moving up and down, and that is essentially showing the oscillation pattern on the sun's surface. Now, to observe these, you need to have a continuous data set, a long time series, and for that there were 6 identical instruments have been deployed at 6 different locations. One is in Udaipur, then Tenerife, then Africa, then the US and Hawaii, and then Learmonth. And that is essentially to cover the whole longitude, so that you have a continuous observation of the sun from different locations. The other way you could do is to go to space, and the Solar and Heliospheric Observatory SOHO was put into space in 1995 at the first Lagrange point L1, which goes around the sun with the earth, so that you have a continuous observation. There is no night sky. Now, it is being done by the Solar Dynamics Observatory, which was launched in 2010. It is a continuous observation now from includes SOHO and Solar Dynamics Observatory from 1995 till today, and a lot of information has been obtained about the solar interior. Now, if you have these oscillation patterns observed on the sun's disk, essentially sun is a sphere, then you need to make a mathematical model of it, right. And the eigen oscillations of a sphere can be described by spherical harmonics. In spherical harmonics, each oscillation mode is identified a set of 3 parameters, N, L and M. N is essentially telling you the radial nodes, which is in the radial direction. L is the number of nodes on the surface, which is showing on this particular surface of the sphere, and are this way, are connecting the poles, and M is the number of nodes which is passing through the poles. So, only from north pole going all the way till the south pole, that is represented as M. If you can put it in a more firm footing, what you have is the L is the number of node lines on the surface. So, for example, here what is shown is you have the sphere and L is on the surface, and if you this is represented as L equals to 6 and M equals to 0, because there is no node which is essentially in the left image, there is no node which is going from pole to pole, but in the middle for L equals to 6, M equals to 3, you have 3 going in the horizontal and 3 going from pole to pole, where in the last one is L equals to 6 and M equals to 6. Now, look at the sun's surface, which is again an observation taken from SOHO MDI. You have these oscillations taking place at each point. Now, depending on how many or how good the resolution of your instrument is, you need to have that large value of L to cover up the whole solar sphere. Now, if you do that for long term observations, you find good signal to noise ratio, then solar eigen mode, if you observe these at each position, you can do a 3D Fourier transform, where on x axis you plot L values, and on y axis you have the frequency, what you find is that the power is seen only in certain regions, that is, for a given k only certain frequency contain power, right. So, you see that everything is confined into different well defined regions. At a fixed L, different frequencies show different power, and each of these regions belong to different order n, that is number of radial nodes. So, what you have, if you go from top to bottom to top, where n, the radial mode 0 is the bottom one, which we call them f mode, which is essentially seen on the surface, and then you go deeper inside, you are increasing the n values. What you also see that there is a large value of L available, but higher in n you go, it reduces, the power or the signal reduces. The lowest lying ridge is due to the fundamental mode, which is f mode, because f is for fundamental, and that is what you see on the surface. Only small values of n, but intermediate to large value of L is observed, and that L values depend essentially on your spatial resolution, that how well you resolve these structures on the sun. Now, P modes are influenced by the condition inside the sun. They carry information on sound speed and on plasma flow, and by observing these oscillations on the surface, we can learn about the structure of the solar interior. Now, solar eigenmodes can be of three types: P mode, F mode, and G mode, and only P and F modes are observed by uncertainty. We for sure know that P and F mode are there. The P mode, so for any wave you need to have a restoring force. For P mode, the pressure is the restoring force, and that is why the name. They travel with sound speed, and they live longest where the temperature is lowest, because the CS, sound speed, is proportional to the square root of temperature, and therefore, they are more confined towards the surface of the sun. If you go deeper, the temperature starts to increase. The F mode, for which the restoring mode is gravity, that is restricted to the solar surface, and they decay exponentially with depth, propagate on the solar surface, and they are like waves on water surface. So, they are just going up and down on the surface of the sun. Both P and F mode are excited by turbulent convection, mainly granulation. As you could see, the granulation power is coming and perturbing, and they are also producing waves. G modes, however, the restoring force again is gravity, but they penetrate deep inside the sun. Now, here is a sketch for P mode and G mode, or rather a simulation. In left you see P mode for different n and L values, and in the right panel you see G mode for n and L 10 and 5. So, higher the n you are going deeper, and higher the L you are resolving it better. What you see that the P mode propagate throughout the solar interior, but are evanescent in the solar atmosphere. G modes, they propagate in the radiative interior and in the atmosphere. Their amplitude drops in the convection zone, because essentially there is a lot of things going on in the convection zone. There is no stability, the density blobs are rising and falling. So, that actually prohibit the G mode to travel into the convection zone. G modes are expected to be the most sensitive to the very core of the sun, because that is where they are probing into, while the P modes are most sensitive to the surface of the sun. And the current upper limit on the solar interior, G mode, lies below the 1 centimeter per second. So, the resolution or the accuracy in your measurement is up to a level of 1 centimeter per second. So, there have been multiple claims of having detected the G mode, but due to these limitations it has always been or is still being debated. Now, what are the applications of helioseismology? By observing these waves, can we apply it to understand what the solar interior is like? So, there are two ways you can apply. The global structure you can look at, for example, look at the radial structure of the sound speed or the structure of the differential rotation, that we call a global helioseismology, that gives the radial and latitudinal dependence of the solar properties. Or you applied local helioseismology, that in principle allows imaging of 3D imaging of the solar interior. It also lets you see through the interior of the sun and then you can look at various properties like how the magnetic field is generated, how is the magnetic field is popping up, and so on and so forth. We can apply helioseismology. One of the application is to look at the sound wave and its radial structure. So, what is plotted in this is the distance from the solar center on x axis and delta c square over c square on y axis. That is the relative difference between the sound speed square as a function of radial distance from the sun center. What we find that typically there is very good agreement. So, the differences are tiny, but there are three different areas where, given that how close the modeled and the observed sound speed, relative sound speeds are, there are three areas where differences are rather large, and those areas are the solar core, as you can see here. The other area is the bottom of the convection zone, where the differences are quite large, it is increasing and then it is decreasing again, and then on the solar surface, where you have this area where the sound speeds or the waves are observed on the surface. So, the three problem areas are the solar core, the bottom of the convection zone, and just at the surface, and that requires work, and that is one of the main reasons that we want to observe G mode, because that will give information which will then correct the discrepancy at the solar core, and also to see where and how the G mode propagate into the convection zone. If it does, then that also will give you an idea about what is happening in the convection zone, at the bottom of the convection zone. Let us look at the solar internal rotation. You know that we talked about earlier that the sun rotates faster at the equator and then slower at the pole. Now, using helioseismology, we can look at how does the sun's rotation change as we go deep inside the sun. Now, until the advent of the helioseismology, very little was known regarding the internal solar rotation. But if you plot again the rotation as a function of distance from the sun center, what you find that the rotation rate is highest at the equator, and you go further away from the equator 15, 30, 55, 45, 60 and 75, the rotation rate decreases. But what you find exactly at the bottom of convection zone, where the convection takes over as an energy transfer mode from radiation, below that in the radiative zone, the sun's rotation change abruptly to a solid body rotation. So, the convection zone rotating differentially, whereas the core and the radiative zone is rotating as a solid body. That provides a very strong shear at the bottom of the convection zone, and that has very strong implications on how the sun's magnetic field is generated and various other structures then appearing on the sun's surface. The local helioseismology is very useful for looking at the convection, supergranulation, because then that essentially allows you to perform a 3D imaging. So, for example, if you can use this local helioseismology, and there are various methods which you can apply: time distance, ring diagram, holography, direct modeling and Fourier-Hankel methods. You can address a lot of issues which are related to dynamo and global dynamics, rotation, large scale convections, far side active regions, and prediction of space weather, because that is particularly of importance, because if you can do this far side active region imaging, then you will be able to say that a solar structure which is prone for eruption will be coming on the visible side of the sun's disk, which can be seen from Earth, and if that shows any activity, it could be problematic for space. Then one can be planned if this prediction based on this prediction for the space weather. So, solar interior, we looked at the neutrinos and looked at the standard solar model. In a similar way, the helioseismology can be looked at. Helioseismology could be used to look at and confirm about the various physical processes which is being predicted from the standard solar model and re-verified. Thank you very much.